Hey everyone, and welcome back to The Explainer. Today, we're diving into something that's honestly a massive breakthrough for decentralized AI. Imagine for a second that you could cut the cost of validating decentralized AI compute by over 70%. And the kicker? Doing it all without actually needing an answer key to check the work. Well, that's exactly what a newly published framework called PoQ-Judge is pulling off. If you're out there building, running, or even just following decentralized LLM networks, you already know that verifying the quality of untrusted compute is a huge bottleneck. So today, we're going to break down the actual research behind PoQ-Judge and see exactly how it solves this.
So here's our roadmap for today's explainer. We'll kick things off with the proof of quality problem, introduce the PoQ-Judge framework, and then peek under the hood to see how it's trained. Then we'll get into the cascade evaluation cost cutter, weigh the architectural trade-offs, and wrap up with a checklist for building your own decentralized network.
All right, let's jump right into section 1, the proof of quality problem. Okay, so here's the fundamental roadblock. In a decentralized LLM inference network, you're distributing compute jobs across this massive pool of nodes. Sure, some might be trusted, but a lot of them are untrusted or just semi-trusted. So the big question is, how do you stop a node operator from just submitting absolute garbage? Giving you low quality, super cheap to generate outputs, but still claiming they put in all this heavy computational effort to get their payout. You absolutely need a way to verify their work. But you can't just run their same prompt through some massive, expensive model to double check it, right? Because if you do that, it literally defeats the entire purpose of decentralized distributed efficiency.
And that brings us to proof of quality, or PoQ for short. In a perfect world, a proof of quality mechanism has to be two things. It's got to be lightweight, and it's got to be reference-free. Traditional pipelines, they usually rely on ground truth references, which is basically having an answer key, or they rely on running a super heavy LLM as a judge model. But in a decentralized setup, both of those approaches just completely break down. You don't always have a reference answer lying around, your latency constraints are incredibly tight, and honestly, you just can't afford the massive computational overhead just to grade the homework of your nodes.
So we clearly need a new way to judge outputs, which leads us to section 2, introducing the PoQ-Judge framework. Okay, I want you to focus on this specific number, 0.747. The PoQ-Judge framework trains these dedicated judge models to score a query and an output pair completely without any reference answers. And the crazy thing is, it actually works. On a held-out test set, the best-performing architecture in this framework hit a 0.747 Pearson correlation with ground truth proxies. Basically, that means its scores matched up incredibly closely with what a human or a premium model would say. Just to put that into perspective, this reference-free model is actually outperforming older evaluators that did use references. It's just a massively strong signal that you don't always need the answer key to know if an answer is actually good. So how on earth is it doing this? Well, instead of just memorizing specific reference patterns, PoQ-Judge is engineered to learn what they call latent quality dimensions. It looks directly at the query and the generated output, and it learns what a high-quality semantic response actually feels like for that specific type of prompt. Because it operates entirely without references, it can just drop seamlessly into decentralized validation loops where those ground truth answers are missing or where they're intentionally hidden to stop data from leaking to the node operators. All right, moving on to section 3, training without ground truth references. Let's look at how they actually built this. Because the obvious question for any ML engineer watching this is, how do you train a model to evaluate quality without an answer key? Well, it all comes down to a really targeted two-stage training pipeline. Step 1 is a broad baseline alignment using the ultra feedback dataset. This gives the model a solid foundational understanding of how to just follow instructions across a bunch of different tasks. But stage 2 is where the real magic happens, fine-tuning on GPT-labeled in-domain data. This stage basically grounds the judge's scoring in very task-specific quality signals. It's teaching the model to look for those subtle nuances that prove actual, high-effort inference behavior, instead of just, basic fluency. And that sets us up perfectly for section 4, the cascade evaluation cost cutter. This is where network operators are really going to want to pay attention. 72.7%. That is the exact amount of evaluation compute cost you can eliminate using this framework, with a technique the researchers call cascade evaluation. And the absolute best part about this? You get this massive cost reduction with only a tiny, very modest drop in evaluation quality. Let's break down exactly how it pulls this off. Think of cascade evaluation kind of like a medical triage system, or even a bouncer at a club. If you're routing every single output through your heaviest, most expensive judge model, which would be 100% cost, you are just burning resources. Cascade evaluation fixes this by chaining lighter, cheaper evaluators first. If an output is obviously just total garbage, the lightweight model catches it and immediately tosses it out. It just fails the early threshold. Then only the really complex, borderline, or super nuanced cases get escalated up the chain to the heavier models for a deep semantic analysis. By doing it this way, your average inference latency stays predictable, you maintain the correlation you need for fair payouts, and you're operating at just 27.3% of your original cost. It's brilliant. But of course, there's always a catch. Let's get into Section 5, Architectural Trade-offs and Limitations. Because no single model fits every use case, right? When you're building a decentralized network, you really have to balance your specific hardware realities with your validation needs. This information is an absolute goldmine for developers. PoQ-Judge evaluates 3 distinct architectures. First up, the text CNN. It has the absolute lowest compute footprint, which is perfect for low-tier nodes, but it only really captures shallow syntactic and lexical patterns. In the middle, you've got the mini LM cross-encoder. It analyzes the prompt and response together, offering a moderate footprint but with strong semantic alignment. It's a really great sweet spot for mid-tier nodes. And finally, at the very top end, there's Dudarik. It gives you the highest correlation scores through deep semantic analysis, but it's heavy. It eats up way more VRAM and processing time, so you'd only really reserve that for your high-capacity validators. The beauty here is you get to map the architecture directly to your node hardware. Now, we do have to talk about the limitations. To be fair, the paper is super transparent about this. Performance varies wildly depending on the actual task type. For question answering, the framework is incredibly robust. That's where we get that awesome 0.747 correlation. But for summarization tasks, the correlation definitely drops. The researchers note that current ground truth proxy datasets for summarization just lack the granularity needed to train reference-free judges effectively right now. So if you're evaluating summarization, you really need to treat these scores as directional indicators rather than hard, punitive rules. Okay, so how do we take all this theoretical research and actually use it? Let's hit Section 6, Building Your Decentralized Network. If you're an architect for a decentralized network, here is your brass tacks immediate deployment checklist. First, enable cascade evaluation on day 1 to lock in those 72% cost savings. Second, map your nodes to either mini-LM or dBERTA based on what their hardware can actually handle. Third, as your pool scales up, make sure you're closely monitoring online calibration metrics to keep things consistent. Fourth, and remember our warning from earlier, supplement your summarization workloads with task-specific human review or domain-grounded references for now, at least until the proxy data catches up. And finally, always pin your judge model versions in your deployment manifests. You definitely don't want unexpected regressions when the framework eventually updates. I really want to highlight this specific insight before we wrap up. Because PoQ-Judge uses online calibration, it identifies semantic quality as the dominant scoring dimension. Why does that matter for you? Because it means the system actively avoids being gamed. A malicious node operator literally can't just submit a fake answer that has high surface-level token overlap to trick the system. The judge is actually weighting the features that matter, the true semantic meaning. That makes it incredibly robust for distributing your proof of quality rewards securely and fairly. Which leaves us with one final, kind of provocative thought. We know this framework is an absolute game changer for question answering, and we know cascade routing completely solves the cost issue. The last real bottleneck is the data itself. So the big question is, when will reference-free proxy datasets for summarization finally mature to the level of QA? Because honestly, once they do, frameworks like Q-Judge aren't just going to be a useful tool. They're going to become the absolute, unavoidable standard for all decentralized compute. Definitely keep a very close eye on this space. Thanks so much for joining me on this explainer, and keep building.